In the next couple videos, I want to give some other applications related to sorting. Specifically, this video gives another way in which we can conveniently use the generic merge subroutine, also used by merge sort. This is using it in order to implement a set data structure. Now, a set is a collection of unordered, distinct objects, so there are no two objects of the same kind in a set. While there's no inherent ordering of items in a set, it will be helpful for us to maintain an order to them just in order to efficiently implement set operations. Now we'll see how to implement the three main set operations: union, intersection, and subtraction. So as a quick reminder here, the union of two sets, if we have, let's say here is the set A and here is the set B, the union of these two sets consists of every element that's either in set A or in set B or in both of them. The intersection of two sets, again, keeping that the left one is A and the right one is B, the intersection is just only those elements that are in both set A and in set B. And with set subtraction, we have A minus B would be, if the set on the left is A and the one on the right is B, A minus B would be anything which is in A, but not including anything which is in B. So it'd be just this portion of our set. And we can implement all of these using the generic version of that merge subroutine that we had used in merge sort. And we want to implement all of these so that the runtime is no more than however many elements we had in A, plus however many elements we had in B. So this would be a linear runtime with respect to the sizes of those two sets. So we're going to store a set in a list, just with an ordered list. Now remember, a set doesn't have any duplicate items, so we're only going to store distinct elements. And while a set itself isn't ordered, we're going to internally maintain an order to it just so that we can efficiently implement these set operations following just any ordering. So if these were numbers, we could put this in ascending order, for example. Then the amount of space that we use is linear with respect to how many items we have, because we have just one space for each item that we have to store. And we can use that generic merge subroutine. So we had used this before in merge sort in order to take two lists, A and B, that were already sorted and then put them into one large sorted list. And we're going to use the same idea here to take now two sets, which are represented as sorted lists, and put them into one set based on which operation we're doing, taking either items from A or from B or from both of them or from only one of them. But this is that generic merge algorithm. We want to form some sequence S. This is what we're going to return. And we do so by going through the items in A and B. If A and B are already sorted, we take just the first item of A, let's call it little a, and the first item of B, we'll call it little b, and then we compare them. Either one of them is smaller or they're both equal. In either case, we remove whichever one is the smallest one. If they're equal, we remove both of them. And then we perform some action. So what we have here shown in blue is just a generic operation which can change based on which of the set operations we're implementing. And then once we run out of items in one of our lists to compare to, then all of the items in the next remaining non-empty list we know are the next smallest items. So with the generic merge, we can choose to do some action if A is smaller, if B is smaller, or if they both have the same value. And we're going to use the same approach to implement the three set operations and just perform slightly different operations in each one of these cases, if A is smaller, B is smaller, or if they're equal. So for example, let's look at union. So again, this is, with union, we want to take anything which is either in A or in B or in both of them. So in order to implement this, we're going to again check, okay, here's the first element of A and here's the first element of B, and we're going to compare them, and as we go through them, we're going to remove items from A and remove items from B so that the first item becomes, in a list, becomes the next one. And then just repeatedly check to see comparing the first item of each of these sequences, which one is smaller? Is A smaller, is B smaller, or are they equal? With union, we want to take our resulting sequence and make it include anything which is in either A or in B. So whichever one is smaller, whether it's from list A or list B, we're going to include it in our sequence. So if A is smaller or if B is smaller, we're going to copy that item, put it in our sequence, and then remove it from the list either A or B, going to the next element of A or B. But if they're equal, then that means this item is in both sets, and we're going to include that item in our resulting set, which is the union of A and B, but we're only going to include one of them. Doesn't matter which one we pick, either A or B, because they're the same, but we're only going to include one of them because our set contains no duplicate items. So for example, if we have these two sets A and B, again, we are maintaining an order to them, even though sets themselves don't have aren't ordered. We're just using an order to them to implement these operations more efficiently. And we'll start with the first element of each of them and compare them. And they're the same, so we're just going to include one of them in our list S. And we move to the next one. We take whichever one is smallest. We compare the first item of each list again, so we'll compare 6 and 7. 6 is smaller, so we take it. Now we compare 7 and 7. That means that this item belongs to both list A and B, so we're going to remove it from A and B, but we're only going to include one of them in our set S. And then we keep moving down this list one by one, taking the next smallest element in order to implement set union. And in doing so, we implement union in linear time. So we went through every item in A, which if we had this many items in A and this many items in B, then our total running time was big O of NA plus NB. Just because we went through each of these items here and each of these items here. And we can do a similar thing for the other set operations for intersection and subtraction. So for example, we had those three cases. If A is less than B, if they're equal, or if A is larger than B, meaning B is the smallest one. And we just saw in the previous slide, if we're implementing set union, then if A is smaller than B, we take A. If they're equal, we'll take one of them, doesn't matter which one, but we only take one of them and move on. And if B is smaller, we take B. And by doing so, we take any item that belongs to A or B, or belongs to both of them, but we're only going to take one of them if it belongs to both of them. And with intersection, again, the intersection of two sets, we only want to include items which are in both of them. So if we find some element which only belongs to A, so A is the smaller one, then we don't include it. But if it belongs to both of them, we include it. And if it belongs to only B, we don't include it. And with set subtraction, say we want to take A minus B, we'll definitely include those items that belong in A, but we won't include any items which are in both of them, meaning it belongs in B, or any items that are exclusively in B. And we can implement all of these methods in linear time. So this is just one other way that we can use that generic merge algorithm, like we saw it used in merge sort, although applied to a slightly different setting and applied to implementing a set data structure.